And so the point is, we're going to post immediately the slides of the invited speakers in this unofficial website. I also want to point out that unlike Monday and Tuesday, today's Wednesday, that we're not ending at 3:30. Come back at 4. We'll go out for a brief break, come back for our final session, which has 2 methodology talks and then I think it's going to be fascinating discussion, panel discussion, and we'll sit here, and there will be time for audience participation in that discussion. So please come back and try to synthesize what we've learned in the last few days. Also, I remind you on the back of the sheet, if you don't have the sheet, there's some up here, and there's some back in the back seat there. There's other parts to this meeting. There's the poster session downstairs with dozens of posters, and if you haven't seen them all, go back down and enjoy them. And tomorrow is the Software Hack Day. It's also called the Splinter meeting here. It starts at 9 a.m. It will be in room 324, which is one of the smaller rooms over there, with tables. And in the morning, there'll be brief, informal presentations of software. Many of the software packages you've heard about here, or you see down in the posters, will be presented. Then everybody go to lunch. We come back. And then there's no presentations, it's a hack day, okay? All the software presenters and maybe a few more will be at the tables, and there'll be little labels, and you can go and visit and learn some Python or learn some R, or just learn from whoever you want to learn from, or talk to your colleagues. So that's the Splinter Day, and then there's some other things as well of the Splinter meetings coming up at the end of the summer. So please have one of these around to get the lay of the land. Okay, I'd like to invite Phil Gregory to chair session number 6.
Testing. Oh, good. All right, well, our first speaker, let's see, I got the
It's a tricky name.
Andras Zsom, yes.
Andras Zsom.
Andras Zsom, okay. And he's going to be talking about a population-based habitable zone perspective.
Let's see if I can do this.
Click on it. Yep. It's speaking to the phone, it doesn't broadcast.
So, aloha everyone. Thanks for coming. So, I can get it. So, my name is Andras Zsom. I'm a postdoc at MIT, and today I will talk about the population-based habitable zone model. And with this model, I will illustrate how atmospheric characterization will help us a lot to identify habitable worlds. And I will also tell you what I believe is the greatest challenge in identifying these habitable worlds. So planet is in the habitable zone if it has liquid water on its surface. So this is primarily a surface pressure, surface temperature condition. And what you see here is the phase diagram of water. You have temperature on the x-axis, pressure on the y-axis. So we want to find exoplanets where the surface pressure and surface temperature falls within the green area on this figure. And for reference, I also included some solar system planets like Mars, Earth, and Venus here. And Earth, of course, safely in the habitable zone. So yeah. So traditionally, the habitable zone is covered in the following way. Let's take a planet with some atmospheric, surface, and geophysical properties, and let's see how far we can move it around different stars to still have liquid water on the surface of this planet. And so this is most often calculated for Earth, but we can also take, for example, Mars or Venus. We also know the atmospheric geophysical properties for these planets. And we can also calculate what is the habitable zone for these planets. That is to say, the habitable zone is planet specific, and it changes a lot if you change atmospheric and geophysical properties on the planet. So what determines the surface climate? That is determined by the stellar properties, the luminosity, stellar temperature, stellar mass, for example. And this, we have some observational constraints on the stellar properties, right? The planet's orbital parameters are also very important. This determines how much stellar flux arrives to the top of the planet's atmosphere. And we also have some constraints on observational constraints on these properties. What we don't really know is the planet properties. We don't know the atmospheric surface and interior properties of this planet. So basically what I want to do here is to see what can we tell about the surface climate if we know so little about the planet properties. The way I do that is that I want to describe the habitable zone as a probability function. I want to know what is the probability that this planet has liquid water on the surface, given the stellar type, the planet radius, and the stellar installation. And once I have this BAC term, I want to find out what is the occurrence rate of habitable zone planets. So the basic concept is to treat the stellar and planet properties as random variables. And some of these random variables are observationally constrained, and for those I just sample from the observed distributions. Other parameters are unconstrained, and for those I generate a large number of diverse probability density functions, and I sample from those. Once I sample all of the variables, I use a 1D climate model to check what is the surface climate on the synthetic exoplanet, and then I repeat this several times, and in this way I generate a synthetic exoplanet population, and then I study the subpopulation which can have liquid water on the surface. So what kind of planets are there in this population? It's really diverse as I could think of. For example, the planet core can be made out of anything, any combination of water, silicate, and ions. The two extreme cases are pure iron and pure water cores. The atmospheres can be nitrogen, CO2, or hydrogen dominated. Surface pressure can be anywhere between 1 Pascal, which is 10 to the minus 5 bars, to 100 bars, which is a very wide range. The surface albedo for planets around M-dwarf host stars is between 0 and 0.4. M-dwarfs radiate in the infrared at longer wavelengths, and in that wavelengths, the albedo of ice is not 1, but is reduced. So this is this albedo effect that we need to account here. The relative humidity of the atmosphere can be anywhere between 1 and 100%. So there are all kinds of planets in the distribution. So here I show a result figure. This figure shows the average probability that the planet has liquid water on the surface for M-dwarf host stars. The planet's radius is on the y-axis in units of Earth radii, and the stellar installation is on the x-axis in units of solar constants. So in every grid cell that you see on this figure, there are roughly 1 million synthetic exoplanets, and basically I just calculated what fraction of those have liquid water on the surface, and that fraction that is shown here with the contour levels. So you see a few things already on this figure. First of all, if a planet is larger than roughly 2 to 3 Earth radii, there is not a single synthetic exoplanet which is habitable. That's because such planets are expected to be mini-Neptunes without a solid surface. Other thing is that habitable zone has an inner edge. If planets receive more than roughly 2 solar constants of insolation, the surface temperature is too high, and such planets again cannot have liquid water on the surface. And in this intermediate regime, that's interesting for us. Some fraction of exoplanets could have liquid water on their surface if they have the right type of atmosphere. So let's take a specific example. Let's assume we discover an Earth radius planet that receives exactly 1 solar constant insolation around an M-dwarf star, and the other parameters are observationally unconstrained. So this is like what we know currently about exoplanets, more or less. And we are at this point, and you can read out that the average probability is roughly around 20–30% that this planet is habitable, but the uncertainty is large. So PHC can be anywhere between 0 and 60%. So we have very vague constraints on PHC, and that's because most of the atmospheric properties of the exoplanet are observationally unconstrained. So the model is adaptive. That is, as we have more observational data coming in, we will be able to incorporate that data in the model, and we will be able to see how our knowledge of PHC increases over time. And to illustrate this, I'll show you an example, which is related to the James Webb Space Telescope. So let's assume we find this planet before JWST is launched, and then we can follow it up and measure its transmission spectra with a high signal-to-noise ratio. And from this spectra, we can retrieve what is the planet mass, use a paper for that. We can also constrain the atmospheric composition. And what we see is that it has an intermediate atmosphere, it's Earth-like atmosphere. It has an Earth-like CO2 mixing ratio of 400 ppm, and there is no hydrogen in the atmosphere. What we might not know from the transmission spectra is the relative humidity. That's because that's a property which is close to the surface, and we might not be able to probe so deep in the atmosphere. For similar reasons, we might not know what is the surface pressure on the exoplanet. If we see a cloud deck, we will not be able to distinguish that from the solid or water surface. We will not know the surface albedo of this exoplanet because transmission is not sensitive to that. So the question is now, would you take your backpack, take Starship Enterprise, and colonize this planet? And of course, if I ask like this, the answer is no. So pH goes up. It is now 10 to 80% given the new observational data. But it is still very uncertain. And so the main reason for this uncertainty is that we don't know what is the surface pressure on this exoplanet. It matters a lot if the pressure is 0.11, 10, or 100 bars. That determines the surface climate very, very strongly. Okay. Yeah, so for similar reasons, you can also imagine that the occurrence rate is weakly constrained right now. So I used the data set from Dressing and Charbonneau, small planets around small stars. And based on that, what we can tell right now is that the occurrence rate of habitable zone planets will be anywhere between 0.001 and 0.3 planets per star. And we need more observational data, more atmospheric information to constrain this number. So what I showed you here is this PAC model to estimate what is the probability that the planet has liquid water on the surface. I showed you how atmosphere characterization will help us to improve our knowledge on PAC. And what you also see is that we really need to know what is the surface pressure on these exoplanets. It has a very strong impact on the climate and on the habitability of exoplanets. The model I used is available on GitHub. It's called Hunter, Habitable Zone Uncertainty Estimator. And so you are welcome to download it, plug in your own observational data, or try different PDFs and see how the results change. Thank you very much.
Well, we have plenty of time for questions.
Why don't you use the transmission spectrum, emission spectrum?
Because right now, you know, I wanted to use a data set where we have planets. Oh, you mean for the atmosphere characterization?
Yeah.
Oh, yeah, you can use emission spectra as well. So I know that for Earth, in emission in the infrared, you don't really see down anywhere near the surface. That is, you probe
In the infrared, you can.
in the infrared.
Yeah.
What about thermal emission of our own atmosphere? In reflection,
You can see out, so you can see in.
Okay.
Yeah.
Yeah, maybe. Yeah.
No, the satellites sound the Earth's atmosphere using the CO2 band.
Okay.
You can see all through all the levels. Yeah, I mean, it would determine the pressure too.
Okay, yeah, that would be great.
Hi, Andras.
Hi.
Good to see you.
Good to see you.
Could you go back to, I think it was on the third slide when you showed the, keep going back. No, keep going forward, one more, right there, one more slide. There you go. Okay. So what I see here is that while you have the able to put the boundaries up and down, what you have on the right side introduces a tremendous amount of degeneracy. And so could you comment on that, and how do your results depend on this degeneracy? How do you take them?
What is the degeneracy exactly?
Well, so the mixing ratios, and so take any of the mixing ratios. Just by slight variation of mixing ratios, you can get similar. You can get that Bill's square right where it is by changing the slight mixing ratio of the N2O2 CO2 and all that.
Oh, so the square in there, right, just shows you that the planet has one Earth radii and this is one solar constant.
So they have, what I'm saying is that for that square, they have stability. will depend on the properties of the atmosphere.
Yes.
And those, right, and those mixing ratios introduce a big parameter space.
Oh, yeah.
Introduce degeneracy.
Yes. So what I find here is that roughly, let's say, 30% of those exoplanets can have liquid water on the surface. Right? The other 60%, 70%, they are either too hot or too cold to have liquid water on the surface. So what I show here is that depending on what kind of atmosphere you have on the planet, you might or might not have liquid water on the surface. So we need to know the atmosphere properties if we want to know whether there is liquid water down there. Yeah.
Any other questions?
So looking at this plot right here, the fractions of habitability you get, it looks like you're never going to go about 40%. Are there any other spectral types of stars that you can put in there, or any other potential input fluxes or radii where those that fraction gets higher? Could potentially say with more certainty that if you found a planet of these properties, it would actually be useful?
Yeah. Okay, so this is the same figure but for solar-like stars. And here you see it looks slightly different than for the M-works, and this figure also doesn't have PAC larger than 40%. What you see here is that the inner range is somewhat closer to the host star. That's mostly because Rayleigh scattering of the atmosphere has to reflect some of the incoming radiation back to space. And also the surface albedo range here is wider. It's between 0 and 1 because of the ice albedo.
Okay.
And then wave.
Hi
Hello.
there.
So there's about 40 people who may be watching.
All right. Thank you for joining in.
Speak into the phone. Please.
All right. Yeah, well, thank you first of all for the organizers for inviting me here to talk about spectroscopy. Initially, the organizers asked me to talk about degeneracies in exoplanet spectra because they sounded a bit too pessimistic. I put an overcoming in front of it and basically focused the talk a bit about what are degeneracies, but also what can we do to get out of them. But before I go into the details of what exactly the information content of different spectra is, I want to point out a bit on why we're actually doing this. Because in the end, we might not be interested in every detail of every single molecular profile. What we're actually trying to answer is some very fundamental questions. So for example, for the giant planets, we want to find out what is the origin of these giant planets. A question that is basically as old as I am is whether they form through core accretion, disk instability, or cloud fragmentation, like stars do. And then also, especially for exoplanets, we have now a population of quadruplets we can study, and we also have a population of directly imaged giant planets at wide separations. So the question is, do they have a common origin? The hope is that some of these questions can be answered by determining the elemental compositions of these giant planets. And in particular, when you compare this to the solar system, we don't even have the oxygen abundance of Jupiter right now. So getting this for exoplanets would be extremely helpful, and for population even more helpful. So a number of theories have been put forward. One is, for example, by Oberth in 2011, that suggested that if giant planets form through core accretion, then the carbon to oxygen ratio in their gas envelope could be different from the stellar value, and would reflect basically where the planet has accreted most of its gas. So, and the reason for this is that as water and CO2 and CO condense at different temperatures in the protoplanet disk, so at different radii from the star, it is conceivable that the protoplanet disk, the gas in the disk, has a CO origin that increases with radius. Now, this is only one theory. There's a ton of other theories out here, but I guess the basic idea stays the same. If planets form through core accretion, then first, basically, they form solid cores that accrete gas then. So kind of these things get separated. And it would be highly surprising if in the end the planet comes out with CO ratio is identical to the star. Now this was, while these theories are very interesting in their own right, they were initially motivated by the detection of carbon-rich planet, POS-12, and also the claims of low abundances of water in giant planets. The thing is, what I think today, we don't really have any detected high carbon oxygen ratio, so it's worth looking at this again. Then on the other side, there are the small exoplanets, what we call super-Earth, or mini-Neptunes, and they're an even larger mystery. Not only do we want to understand how they form or where they come from, but also, first of all, we need to understand what they're made of. So who is who of super-Earth? It's a big question. What defines the transition between super-Earth and Neptunes? How small can the gas planet be? The picture of the solar system is obviously not the complete picture. And how big can a rocky planet be? And also for this, again, we need to probe the elemental composition of those planets. In addition to the elemental composition, there's also a lot of topics in the field of atmospheric science that we can study. And this is when it actually comes into the molecular composition. We can look into non-equilibrium chemistry. We can look into thermal inversions, into atmospheric dynamics, and cloud formation. Now, the window to look into those interesting science is exoplanet spectroscopy. And there's actually 3 different types, we have to be aware of this, of how we can study exoplanet spectra. There's first the transmission spectrum, that's when the planet cuts in front of the star. There's the emission spectrum, when the planet goes behind the star, when we observe the planet directly, in the infrared. And then there's the albedo spectrum, when we observe the planet coming out behind the star at visible wavelengths. Now, each of those spectra have very different information content and very different ways of how the information is encoded in the spectrum. The first of them, transmission spectra, is in a way the purest way of getting the composition. And the reason is because we're observing the light that falls through the atmosphere. In the background, we have a white light source, the star. So that's kind of the ideal condition of measuring how much gets absorbed and how much gets scattered. So transmission spectra are highly sensitive to the composition, to haze and clouds. The temperature of the atmosphere is only a secondary effect. It goes into the scalar of the atmosphere, how hot it is, but it's a minor effect, in particular compared to the molecular mass that drives really the scale height much stronger than the temperature. In the past years, we have seen really great improvements in transmission spectra. Here I show, this is from my paper, I show basically a collection of observations of HG2 and 9. And what you can see in particular here is this really robust detection of water absorption in the HST 151 bandmass. And then there's also detections of sodium in shorter wavelengths. Then we also have seen, also in 2014, this is 2013, and 2014, we have seen for the first super-Earth a very precise spectrum. This is GW12NB, and you can see a completely flat spectrum. This spectrum tells us very robustly that there must be clouds. And then we've also detected hazes, where you can see that at short wavelengths, there's much more scattering than we just expect from radio scattering. Then on the thermal emission side, so basically the planet goes behind the star, these spectra primarily are sensitive to the temperature and pressure profile, the vertical structure of the temperature profile. And also the composition and of closed clouds also matter. We have seen, I think as a highlight, a very robust detection of water absorption, even in thermal emission. We have seen from Konopnik et al. And Baumann et al. To exquisite K-band spectra of HR 8799b, this is a direct image planet. And we've also basically had measurements of the Spitzer, and in particular I want to highlight WST12. This is the planet I referred to that has was claimed to have a high C/O ratio based on the single data point up here that is lower, and so it requires basically a carbon-dominated atmosphere. But this is something that we should revisit, because there was basically another paper that looked at it and placed this point much higher. So this constraint of high C/O ratio might not be as robust as initially looked at. And the last, basically the last spectrum is the albedo spectrum. And so far we have only obtained one albedo spectrum. So it's so hard, the contrast is so low. This is HD189, where we basically see 2 data points. So I call it the spectrum, but you can see that there's much more reflection in the blue than there is in the mid-visible. And albedo spectra are highly sensitive to clouds, because clouds can be very reflective. They can be, for rocky planets, they're sensitive to the surface. And of course, there's also an effect of the composition. Now, in this talk, I want to focus predominantly on the on the transmission spectra. The reason is pretty clear, is that we're getting just a ton of data in transmission spectroscopy. So over the past years, I show here a plot from a recent paper that I wrote that basically summarizes the Wildfire Camera 3 observations for 8 on Jupiters from programs from David Singh, Craig Deming, and Jacob Beam. And you can see that all these 8 planets have very robust detections of molecules. And so this is really, in a way, Wildfire Camera 3 has really been a game changer in providing for a large sample robust detections. And then in the near future, 2015 and 2016, that's a large program that is led by me, where we get transmission spectra of 6 super-Earth, so planets in this intriguing 1 Earth mass, 1 Neptune mass regime. This is in cycle 22, and the real question here is to answer whether these super-Earth are predominantly something like a Neptune with a rock, and then, or basically with some core, and then mostly hydrogen surrounding it, or whether they are some kind of completely new type of planet that is predominantly made of ice and water. And then just recently was another program approved by Craig Deming and collaborators. I'm also on this program that basically studies 14 planets in this regime between Neptunes and Saturns. So we have a lot of our Jupiters. My program is going to get a lot of super Earth, and then this program is going to get kind of intermediate range, and then Neptune and Saturn mass regime. But let's now basically go into the details of the transmission spectrum. And before we go into the data, I want to give you some conceptual understanding of what actually is in the transmission spectrum. And I think really I guess what I call the core of all evil is basically, or the root of all evil is basically that we don't measure directly the absorption. So I said earlier, it's the purest way of getting the composition. But what we're actually measuring is the transit depth, or basically the planetary radius. And what you can see in this plot is that, of course, if I increase the abundance of water and methane from the values that you would expect for 1 time solar composition to 50 times solar composition, you can see that you have more absorption in the water bands, you have more absorption in the methane bands, and so, of course, the spectrum moves upwards simply because you have more absorption. So this is a good thing. But the problem is, what makes it much harder, conceptually much harder to understand what the transmission spectrum gives you, is that we don't know the radius of the planet at any reference pressure beforehand. So if you make this planet just slightly bigger, you look at these bands again, and or if you make basically the 50 times solar composition a bit smaller, then the spectrum moves down. And basically you end up with the same spectrum. So you have now an atmosphere that has 50 times more water, 50 times more methane, but the absorption features of methane and water look identical. And this is not only at some kind of low resolution, it's at significantly high resolution that you get this effect. So one thing that you have to take away from this is that, for example, a water feature by itself contains barely any information about the abundance of water. It's very counterintuitive. But I guess that's why I'm here. So because it's such a form, in 2012 I wrote a paper about the uniqueness of transmission spectra. And what I initially did is I did a lot of numerical experiments to try to find out whether we can constrain the water abundance or the methane abundance from transmission spectra. Obviously, the information is not in the feature, but maybe it's somewhere else. So what I took is kind of the most general case. I took a super Earth where we don't know any composition beforehand. I assumed some scenario, volatile scenario with the volatile composition of the Halley comet, and I put this into a retrieval framework that I previously developed. And what you can see is that if you take JWST observations with basically a resolving power of 70 to 300 across this wavelength range, and you feed this in, you actually get nice constraints on the water abundance, you get nice constraints on the CO2 abundance, you get nice constraints on the methane abundance. You can constrain the cloud top pressure, and then you also get some constraint on the planetary radius of the reference pressure. Now this is interesting. Now from this data, apparently we get a unique solution. From just one feature, we don't get anything. So I basically developed a conceptual picture that describes the information in transmission spectra. And I basically want to convey this to you so that we can then go and understand, if we take something away, where are the degeneracies. What I want to convince you is that if you have 3 absorbers, so for example water and CO2 and methane, I call N equal to 3, then this spectrum actually contains N plus 4, so 7 independent pieces of information. And if you have all 7 of them, then you can get the mixing ratios of the N absorbers. You can get up to 2 mixing ratios of spectrally inactive gases, like hydrogen and helium, and nitrogen. You can get the planetary radius and the cloud conversion. So the system is basically a fully determined system. And what are these information? Basically, in every absorption feature, the strongest absorption feature of every molecule, you can take one transit depth measurement. So you do this for the three absorbers. Then one independent piece of information comes either from the radius slope, how steep the slope is, how steep the feature rings are, or how the offset is between features from the same molecule. And this directly gives you the mean return mass. Then we have the transit depth offset of basically how high the slope of the radius scattering is, whether it's up here or whether it's down here. Then we know that the sum of the mixing ratios has to equal 1, and the lowest point in the spectrum basically gives you the best constraint of the cloud pressure. If you have all of them, you get a unique solution. But the problem is it's like a system with 7 unknowns and 7 variables. If you take one out, the entire system falls apart. You can easily still get the relative balance by just comparing this. You can also get the mean molecular mass. But if you basically take one piece out, you're losing the solution. And so what are the sources of degeneracies in real life? One big problem is no coverage of the short wavelengths. So for example, if you only have observations from 2 to 6 micrometers, this is in the infrared, so you don't have the short wavelength side here, then you can make up scenarios, take a nitrogen atmosphere with CO2 and CH4. And if you retreat from this, even if you put really nice observations that are very, very small error bars, you get this strong correlation between the abundance of CO2 and the abundance of methane. This can limit you even from 0.003% to 10%, constraining the abundance of CO2. And methane, the same thing. The second is, kind of related to this, if you have small particle phases at short wavelengths that effectively block the radius scattering signature from molecular radius scattering, then it's kind of the same effect. You can't see the radius scattering slope anymore, or the molecular cost of the radius scattering slope. And this is basically what I show here. Then back to the scenario, if you have 1 times solar composition, 50 times solar composition, there is a difference when they're cloud free down here. So you put kind of the red and the blue one are different. But if you put hazes in, and this is basically the new slope that you get, then the 50 and the 1 time and 50 solar composition looks pretty much identical. We can overcome this in some scenarios, especially for super Earth, if we go into a range where the mean molecular mass changes drastically, because then the feature shape is going to change. This feature shape is only a function of the molecular mass. But the problem is basically for giant planets in particular, that if you're in a region of the parameter space where the mean molecular mass doesn't change, like for giant planets, because they're hydrogen helium dominated, then you stay basically degenerate. And basically, if you go to real data, here again show these 8 transmission spectra, and I call this the narrow wavelength coverage challenge. It's a very current challenge because we have these really nice spectra from where we can run 3. And so the question is, what can we learn from this? What also matters here is basically, so basically when these papers were published, initially everybody of course claimed the water absorption here. But what I want to point out to begin with is that although water absorption has 2 features here, methane absorption has also 2 features. And if you have a high C2O ratio, then this will be methane. And so these bonds could easily be methane. But nobody even addressed this in these papers. The second one is there was a paper by Madison in 2014 that looked at some of the data sets, for example H209, and suggested that the water abundance must be extremely low here because this water feature, while present, very, very robust, is smaller than what you would expect for a solar composition atmosphere. So if you reduce the water abundance, I guess you basically would get a slightly smaller feature. But the problem is also here that we need to worry about clouds. Clouds can also make these features smaller. And then the last one is that because we have only these observations, and let's say this is a water absorption feature, then we haven't detected anything about the carbon. So we can't get any C2O ratio constraint. But this is what we actually kind of wanted to get to say something about how giant planets form. So the obvious solution for this, to break this degeneracy, or break some of the degeneracy, is to get more data. In particular, get something between 2 and 5 micrometer where methane and CO absorb very strongly, then you can simply do C2O is the sum of carbon and the sum of methane. The problem is that we currently have nothing in space that can really do this, at least spectroscopically. There is bits of it, it doesn't really give us what we want. So this would need to wait to JWST. The other solution is basically, and this is where I want to basically talk a bit more about breaking degeneracies or getting more out of the data than we traditionally get, is basically to use our prior knowledge of atmospheric chemistry or atmospheric physics. And this is why I developed what I call the Scarlet framework, it's safe, consistent atmospheric retrieval for exoplanets. If I apply this to the same data set, because we have such a good understanding of how carbon chemistry, carbon, hydrogen, oxygen chemistry actually works, we should include this in the retrieval. Current models basically completely ignore this. So the idea is to find out what can we say about how Jupiter's given all information at hand. This is the data and also our robust prior knowledge. And if you then look at the literature, there's basically, so far there have been two different approaches. They are completely orthogonal to each other. One is self-consistent forward modeling, see what you know from Jonathan Fortney or from Edinburgh Rose or the Phoenix model in Europe. And then on the other side is atmospheric retrieval that completely forgets about the prior knowledge, which is basically what I did before, my client, once done it all. And then also, yeah, there's basically a whole bunch of them. A single Waldman that I didn't yeah. Then let's look at what the advantages and disadvantages are of these models. The advantage of self-consistent forward models is that they use our prior knowledge. They're inherently self-consistent, so the stars make physically sense, and if you match the data, you gain physical insight. The problem, however, is that these models assume that all processes are known without uncertainty. And because this is often not the case, the models might not match the data, and then people start tweaking the models to match the data, but in this framework, you don't have any robust treatment of the uncertainties and degeneracies anymore. Atmospheric retrieval, on the other hand, can robustly treat observational uncertainties. That's why it was invented. But it ignores completely the prior knowledge of chemistry. It completely oversimplifies the description of the atmosphere. Generally, it assumes that the atmosphere is well mixed, although we know from modeling and also from observation of the solar system that they're not well mixed. And the problem is, I think the most fundamental problem is that they don't provide any direct insight into physical processes and the elemental composition. So the idea of the Scarlet framework is to combine those, to have a model that has observational robust, basically robust treatment of the observations, and at the same time use the prior knowledge to get physical insight. The basic concept behind Scarlet is to throw out what is usually the parameterization of atmospheric retrieval, molecular abundances, and temperature pressure profile. What I put in is formation history parameters, this is the metallicity and C2O ratio, so this is the elemental composition, and then a whole range of atmospheric process parameters. Then you fit the data using this kind of model, and you basically gain direct insight into the elemental composition, because you're actually modeling these kind of processes, like the vertical mixing, like the day-night heat transport, you gain information in the atmospheric processes. How is this being achieved? What basically happens is you quantify, explicitly describe your prior understanding of atmospheric processes. This is our understanding of chemistry. You feed in the observations, and then there's a nested sampling algorithm. It's something like an MCUC, basically, and that is surrounding a self-consistent quantity for the chemistry ready for collective model. And what comes out is posterior constraints on the formation parameters and the atmospheric processes. All of this is inherently self-consistent because the model is self-consistent. The challenge is, of course, to identify exactly, or to basically exactly list what are the assumptions here, but at least you're forced to explicitly say what you assume or don't assume. And we have about some processes, like, for example, the chemistry, we have a very good understanding of how chemistry works, even high temperatures. So now I've applied this to this set of Jupiters, Jupiters, and this is basically, I guess, the money part of this application of this paper. Is basically it shows the carbon to oxygen ratio, here representative HD209-458b, and basically it shows the posterior distribution marginalized over all other parameters. That's the metallicity, that's all the cloud parameters. And what you can see is that there's a sharp cutoff at 0.9 C2O ratio. So for this planet, there's absolutely no way that the C2O ratio is above 0.9 in this case. This is actually a very robust finding. So when you look at basically, this is now all the samples that the massive sampling took, and you can see that they're starting to explode everything from extremely oxygen rich, 100,000 times, to 100,000 times carbon rich. And you can see that at 0.9, the solution really drops off from something like a reduced chi-square of 1 to a reduced chi-square of something like 4. These are 30 layer lines, so this is a jump in chi-square of something like 70 or 100. So this is an extremely robust finding that this planet is not carbon rich. Then basically kind of, what is the information in the spectrum? This observation only depends on Y2K3 transmission spectroscopy. This has been shown to be extremely reliable by other projects. For example, Freitag et al. Showed that even if they observe 12 times the same transit, you always are statistically in the same transit depth. And you can see here that what actually drives the solution away from the carbon-rich scenarios is that the carbon-rich scenarios, you would expect methane. But methane, while it causes a feature at the same wavelengths, at 1.15 and 1.4 micrometer, there's no way, even with clouds, that the methane feature is substantially muted at 1.15 micrometer, but not muted at 1.4 micrometer. Whereas with the water feature, you can actually do this. You put clouds in, and you get basically robust, strong detection of a 1.4 micrometer water feature, but not the one at 1.15. So this is how we know that this is water absorption. And from that, basically, we can infer that, or basically the method infers this information it uses, that the carbon to oxygen ratio is actually below 0.9. Now, if you look at all other Jupiters, you come actually up with the same result, with a very similar result. The details are different, but the constraints are slightly different. Here, for example, it's something like 0.8, but in the end, the result is the same. Carbon-enriched scenarios that are dominated by carbon chemistry are completely excluded by the data. And for example, also here was the 12 that was previously claimed to be a carbon-rich planet based on a single data point. Here shows clearly that it's not carbon-rich, and the seed origin is maximum something like 0.85. This is the 99.7%. The other main finding is if you look at the same parameter space in a different dimension, so you marginalize in a different direction, you plot, in this case, the water mole fraction is derived from CTO ratio and metallicity, and on this axis you have the cloud top pressure with high albedo clouds here and with cloud-free scenarios up here. You can see that this is strongly generous, and this is actually pretty straightforward to explain. As you increase the water abundance, the water feature becomes stronger, but if you now move up the clouds, you basically recover the same water feature. That's why you get this strong correlation here. But what you can what's extremely clear here also is that cloud-free scenarios for this planet are excluded. So basically, we know that there must be clouds. There must be somewhere between 200 millibars and somewhere in the sub-millibar regime. This is the correlation that we basically is just in the data. With WASP 12, it's the same story. We know that there are clouds, but this is also strongly correlated with the water abundance. What's interesting to see is, though, that WASP 12 is 2300 Kelvin, HD209 is 1400 Kelvin, so clouds can be present over a wide range of scenarios. What you can also see is that effective particle sizes beyond 1 micrometer are highly favorable by models, by the data. Now let me conclude. I've shown you that visible to infrared transmission spectra, if they are complete, they provide sufficient information for a unique retrieval of the incident composition. That's the good news here. The bad news is that currently we have mainly only narrow spectral coverage. Often there's small particle haze at short wavelengths that inherently lead to degeneracy. And so this prevents us from getting absolute abundances, even for robustly detected molecules. This is something we have to live with if you do a regular retrieval. Now, still, transmission spectra are ideal for constrained nuclear mass because the information is there, and they are also ideal to measure the relative abundances of water, CO, methane, CO2, all these molecules, because the relative abundance information is actually there. And so they are ideal for super Earth characterization. They're also ideal for measuring CO ratios, for example. What is also ideal about them is that their signal strength only goes linearly down with planet temperature. So you can easily probe temperature that a planet that has half the temperature if you can just double the precision. So, and this is for thermal emission spectra, for example, much worse. Then basically, the other conclusions, basically, what I showed is a new framework, what I call Scarlet. It combines statistical robustness from atmospheric retrieval techniques with the sensor consistency and important physical insight of complex fault models. It directly provides elemental compositions that's what we need for planet formation studies, and it also constrains atmospheric processes. And for Jupiters, I've shown that the 8 Jupiters I studied here, they have robustly carbon-to-oxygen ratios below roughly 0.9. And if you put this basically in a very simple picture of planet formation, at least you can exclude that planets have formed out here or formed in a disk where the carbon-to-oxygen ratio is substantially above 0.9. What I also shown is that the water abundances are consistent with solar composition for all 8 Jupiters, so there is no water abundance. And I also shown that thick clouds are very common with a wide range of equilibrium temperatures, at least from 1400 to 2500 Kelvin.
And one quick question. I have two very short questions. The first one is, when you were looking at the different water features of the different Jupiters, and you were saying that it was a shame that a lot of the papers have not mentioned the methane feature. Would you really expect to see methane feature at the temperatures and pressures that you're probing these exoplanet atmospheres? I mean, a lot of them have equilibrium temperature of 1,500 to 2,000 Kelvin for some of the hotter objects. As far as I can remember from the condensation curves, methane is really not an option at this stage.
I think it has nothing necessarily to do with condensation, but what basically anyway, I can answer the question without showing you this slide. Yeah, is basically that everybody assumed it's water because all the models that were calculated by most people that do statistical fault modeling modeled them for carbon-to-oxygen ratios of solar value. And then you expect water. You have more oxygen, the carbon goes into CO, and the rest of the oxygen goes into water. Now, if you have a C2O ratio of more than 1, then basically all the C and O goes into CO, but there's carbon left, and the carbon goes to the hydrogen. That's why you get methane. So basically, this is why you have to, if you don't know the C2O ratio, at least consider the scenario of having methane there instead of water.
Right, and then the other thing was a little bit about the C2O ratio. It was in terms of your Scarlet framework and the results that you showed. How much or how dependent are they on the observations? Because I think on the right-hand side, the retrieval side of the Scarlet technique, you were saying that it's you were sort of taking the observations pretty much at face value and believing them to be true for your technique. Is that correct?
Yes, I'm taking the observations. I guess that's the idea of doing retrieval from the data. I'm taking the observations as they are, and I believe in the error bars, and I treat them as if they are.
Then if those observations weren't necessarily done correctly, as Neil was suggesting in his talk, sometimes depending on how you treat the systematics can give you slightly different measurements. How are they going to affect the results that you've presented here, which have been using the Scarlet method?
I think what is the important key of this study that I did is basically that these results are only dependent on the HST by the MIT. And there is this long history for the last 2 years or so, where people have really repeatedly taken the same spectrum on the same planet and shown that they basically can recover them within statistical error bars every time over and over again. And that's very different, I guess, from what has been done with Spitzer in the past, at least. That there were basically a lot of effects because the systematics in Spitzer are just too much harder. That's not the fault of the people that did it, but the systematics is too much harder, that there was a lot of controversy about this. But with Vertical 3, there has never been any controversy about this for basically 10 planets. And yeah, so I'm very confident that those observations are correct.
Okay, let's thank our speaker again. And the last talk of the session is Measuring Transmission Spectra from the Ground by Andras Zsom. You want to introduce yourself?
I've been talking about measuring transmission spectra from the ground. There's more people involved in this work, but I highlight here my grad student, Mr. Espinosa, and Susanna Björn from the stats department, with whom I work mostly on the statistical aspects, which I will emphasize in this talk. Now, I won't go through the description of transmission spectroscopy. It's been described very thoroughly. I'll just say it's a hard problem. It's a very hard problem. We have time modulations with wavelength on the measured size of a planet. And Neil was talking about systematic effects supported at -3. If you want to do this from the ground, you have to deal with the atmosphere, so you're talking about systematics of order 1, right? So it's really, really much harder. But that doesn't stop us from trying. So for the last 2 years, we've been assembling data as part of a survey called Access, Arizona, CFA, Católica, Exoplanet Spectroscopy survey. Here's the senior conspirators, much of the work being carried out by grad students, Nestor and Ben Rackham. And here I have a sample of planets. This is equilibrium temperature, planetary radius, and Earth radii. The big dots are samples, so we are trying to get 20-something systems with many transits each. In this talk, I'll just talk mostly about WST6. This was a subject pilot program. We're using IMAX on the Magellan telescope to show that this could be done. And then, if I have time, I'll talk a bit about HATS5. That's Hot Saturn, discovered by the HATSAT survey. So, what are the tasks at hand for us? First, measure the size of many wavelengths. The signal will be swamped by systematics. Second, estimate proper uncertainties, because any signal will be small, right? So 10 to the -4 relation. So the significance of any future detect must be properly assessed, otherwise you're going to make wrong inference about the third step, which is interpret the results in terms of atmospheric physics and chemistry. I won't touch this at all, I'll just concentrate on these 2 parts. So this is how the data look in image space. This is the reason we use IMAX. It's a spectrograph with roughly ½ degree on a side. So each of these is a spectrum, and we have our target star, and the wide field of view allows us to get spectra simultaneously for a number of comparison stars. And those will be fundamental for us in eliminating systematics, because those do not have transit. So we use them as probes of the systematic effect. So we get a bunch of images as a function of time. This is how the data look in white line space. So we just sum all those spectra to a single point, we collapse them, and plot them as a function of time. So this is time in hours, and this is just magnitude arbitrary offset, so you can see the light curves. In the case of WST6, which is this data set, we were able to extract 7 comparison stars. And this is our target star. This is WST6. And to first order, they all look the same. Those are the order 1 systematic of the atmosphere, right? You can see here we have some periods, this is air mass, and then we have some periods of strong absorption by clouds. And remember that because you see these features again, first appear and then disappear to high degree of confidence. And you can actually see the transit here, right? WST6 has this decrease here, that's the transit kicking in. So our task is to model this curve, model this map, take it away, model the residuals and correlation in them, and get a transmission spectrum. So this is the one equation I'll show. This is our likelihood. So this is the probability of the data. It's our light curve given a bunch of parameters I will describe. And this probability is a multivariate Gaussian. So we have a mean function. And this mean function is the transit function, which has parameters theta. These are all the transit parameters. And then to take away the systematics, we introduce a linear model with a set of fixed basis functions. So these are the coefficients, alpha, which is the other set of parameters we have to determine. And these are the common systematic signals, right? And this we will obtain from the comparison stars. In principle, the simplest would be to regress the comparison stars as we get. But it turns out you don't need as many. We only have values for 5 components on one side, as I'll show you in a second. And then you have the mean function, and you have a noise covariance or residual covariance structure, which you don't want to assume it's white, because if you make the wrong assumption, your uncertainties will not be right. So this noise covariance will be parameterized by a set of parameters eta, which I will discuss in the follows. So then, once we have the likelihood, we throw in a bunch of priors, and we learn all these parameters through an MCMC. Now, the common signals. As I said, you could take the 7 comparison stars and just regress on them. But what we do is we decompose using principal component analysis, or set. You could use independent component analysis to get the same answer. And it turns out you only need 5. How do we determine this? We just fit out the transit part of the light curve and do 5-fold cross-validation. It turns out that including a 6th or 7th component doesn't really increase the RMS of your linear model, the predictive RMS. So with 5, it's okay. And the first 2 are very easily recognizable in terms of what they are. This is the atmosphere, air mass, and you can see the clouds there, right? So it comes out, of course, very clearly. It's a very clear signal. The second correlates extremely well with the rotator angle. So this is roughly where the target crossed the meridian, and you see the signal very clearly. These are hard to interpret and correlate with some other variables, but we don't really care. We have a set of basis functions, and we just regress them. As for the covariance matrix, we tried different models. We assume a white noise model, but that's the basic, easiest assumption. And these are the residuals. They're clearly correlated, so this is just that model. The level of white noise inferred is about 10 times Poisson. It's just not good. We also explored autoregressive moving average models of degree PQ. The best fitting model was a 2-2. And here you have the transit plus the inferred component from the stochastic process. And this doesn't do good as well. It's hard to tell here, but the model is failing. It's assigning too much importance to the white noise component, which is a telltale sign that it's just not working right. And we also use a long memory process, a 1/f flickering noise model. And that turns out to be by far the best description of the remaining systematics after we model our mean function. So to decide if it's true, we use a bunch of confirmation criteria. This comes out as the best model. And why do we choose these 3 covariance matrices, or these 3 stochastic processes? This is the power spectral density as a function of frequency. And we want a set of covariance matrices that sample different structures in frequency. So the 1/f, it's a long memory process. That's a pole in the origin, actually. That's what defines a long memory process. So very, very long correlations. Autoregressive moving average processes can have lots of power at high frequencies, so very short memory process. If you vary P, this is an arm at 0-1. If you vary P and Q, you can place a peak here, so you have lots of flexibility for shorter memory processes. And then white noise, of course, is just flat power spectrum. That's it. And I think this is a point that it's very important. You really want to match the frequency component of your noise such that your error bars are good. And now we do this whole thing. We learn our parameters in as many wavelength channels as we can, and eventually we get the size from each of these transits. Here are the residuals. You will notice that in the middle, where we have the most signal, the residuals tend to be quite white. And as you go to lower signal part, bluer or redder, you get more correlated noise. So that remaining, that covariance structure is coming from our inability to model the common systematics. There are remaining things that the stochastic process absorbs. And that gets absorbed into the covariance structure and then into the uncertainties. I should say that this, of course, it's an ARMA plus white noise, so this is 1F plus white noise. There's also white noise. And this is the resulting spectrum after a lot of effort. So this is planetary radius, and this is wavelength. Looks quite crummy, but it favors radius scattering slope, featureless spectrum without alkali lines, for example. And it stood there for about a year, and then this was observed by JWST, by Nikolov. And these are the IMAX data points. Oops, sorry. These are the IMAX data points, the yellowish, and the blue and red the same system, the same transmission spectrum observed by JWST. So it's actually fairly consistent. We get more photons because we have a bigger mirror, but we get more systematics, we get less photons. Less systematics. And at the end, we're roughly at the same answer. There's an issue here. Here, there's discrepancy over what you would expect, perhaps, but this is the hardest part for us from the ground. About roughly 0.75 microns, the atmosphere starts to get really, really bad. Now, this is work in progress, work led by Nestor Espinosa, and this is height 5. This is the white light curve. The RMS is 265 parts per million, so quite a nice performance by IMAX. And you will notice that, as opposed to WASP-6, the residuals are quite white. We don't have that component, that 1/f component was necessary for WASP-6. And the reason this is happening, I believe, is 2 years of improving the extraction. So pixel level treatment of the detector, understanding better our instrument, has resulted in improving the precision here. So we're not needing that stochastic components to characterize our poor performance. And this preliminary transmission spectrum is really, really weird. So we have, this is sodium and potassium, and we have these jumps here, and then this kind of mini-ray scattering stuff. We're not holding our breath, this is real, we need more transits. Because despite all of our efforts, as I said in the first slide, these are really tiny signals. We're digging from a lot of systematics. So getting more than one transit is really crucial to believing what you're saying. So I'll finish here with my last slide. So some of my takeaway points. I think ground-based studies can measure transmission spectra despite all the systematic noise, even if using instruments that were not designed for the purpose. I mean, going in, I wasn't really sure this was going to work. You need careful analysis, and you need to understand the instrument. That's really important. Proper characterization of the residuals, so matching spectral characteristics of various makers. Your noise, I think, is fundamental to obtaining the most precise error bar and certainly you can get. And a way forward, Neil already mentioned this. I'm modeling every channel independently. And it'd be nice to model, if I introduce an index alpha for all the wavelength channels, to model simultaneously these, perhaps using hierarchical models, as you mentioned in my talk. Because there's lots of redundant information in all those channels that would strengthen our stereo distributions. And finally, reproducibility. Within the two transits, it's key given the subtlety of the signals. Despite all of our efforts in doing the best we can, we need more than one transit to confirm the signal. Thank you.
That's impressive work on that side. So you mentioned that you have a very good precision and you've done some improvement on the analysis. Can you give us a bit more on those improvements? And also my second question is, how far from photon noise are you for that side? Because that's very impressive, 265 ppm. I've never seen that, so that would be great if you can do that. So can you tell us a bit more?
The pixel level stuff is really lots of details. Characterize the detector well, sometimes the spectrum, for example, sometimes it's moving over a hot pixel. And the first pipelines we have, we kind of ignore that, assuming there are so many photons that who cares. But we do care. It goes in and out of a wavelength channel, for example, a hot pixel, and that gives some weird stuff. So it's many things like what I mentioned. It's a long list of details of the detector and making experiments. We're running now experiments all the time. In September, we observed simultaneously with IMAX and LTS3 and SWOLE all at the same time. Just trying to understand the system better. Regarding HATS 5, just the post-sun noise affords that. So the better you can explain the systematics here.
Okay, thank you. Yeah, I'm going to talk, and I'm also agree with John. It's really impressive work that one thing I'm wondering about is so when you show the spectrum, it also has really tiny errors. And I guess kind of what I talked about earlier is how would I see this spectrum published? And you said you tell me I don't really believe that these things are in there. What should I do? Is there any way for you to provide something where you reliably trust the errors?
No, I trust their advice. I mean, we put lots of effort. So I'll tell you what I trust. This, yeah, sorry, this is preliminary work. This is probably a bit too small. So when I mentioned here, one thing that always worries me is that we're not modeling the wavelength direction in the same level of sophistication we are modeling the other direction. So what do I mean? You know, the error bar here could be okay for the variance at that point, but it could be that you have a strong covariance, right? That we're not modeling.
Right, and this is actually complicated because now it's like, I'm not necessarily planning tomorrow, right? Let's say I'm with, and I use this error, it's going to try to retrieve it. It's saying something like that.
Absolutely, you know, now that I look at it with more care, this is probably a bit underestimated at the moment. Again, it's preliminary, but that's what's coming out.
And this is not only, let's say, from work, I would say.
No, I know.
This is in general, it's a problem.
I completely agree, and that's one of the points I emphasize. And that's why we try to see various structures, because if you say, for example, you have a long memory process as you receive one, and you use, say, a short memory process, that's not necessarily relevant. So estimating, getting the proper uncertainties, in my view, from the point of data analysis, by far the hardest part. Extracting the signal is hard, like getting the proper uncertainties is hard. And that's why it's really, you know, if you observe it 2-3 times, and you start seeing the same pattern over and over again, then that gives you more confidence. So that's why I said despite all the effort we put in estimating the surface properly, more than one transit is still key.
I just want to point out how important it is making this data really
I fully agree.
available for the scientific community.
Suzanne, you still have a question?
I think Bjorn just kind of alluded to it. I was going to say another way of getting confidence in a data set like this is to get other people to analyze it as well.
Yeah. Actually, we haven't discussed that, but I'd be very happy to put up all the images, make them available, do a little archive of the survey.
Okay.
Okay, so we'll thank the speaker again. That ends our session, and I'm told that we return here at 10 after because of our late.